definition. There we go. So let's go back down to my desktop and look at the PowerPoint again. There we go. So what is our objective? Find absolute extrema using maximum, minimum principle number 1. And then we're going to look at another maximum, minimum principle 2 in this PowerPoint. Definition. Suppose that f is a function with domain I. So say the domain is -2, less than or equal to x, less than or equal to +4. That type of domain. Remember from college algebra days, domains consist of x values. So this is the y value of the f function at the critical number. That C really means critical number. That's a candidate for absolute minimum or absolute maximum. So f of c, the y coordinate when the x coordinate is c, is an absolute minimum if it's the smallest y value. So this means this y value is less than or equal to f of x for all x in the interval. So in other words, this is the smallest y value. I mean, it's possible to have more than one place in the interval where you have that smallest y value. Possible to have, you'll have the smallest y value. There's only one of those, but it's possible that that occurs at multiple x's. And this y value at a particular critical number, let's say, is an absolute maximum if it's the biggest y value. And it's possible to have more than one x value, which causes that largest y value. And stop me at any time if you have a question. So let's talk about the extreme value theorem and a continuous function. And a continuous function graphically has no breaks in it. Defined over a closed interval. This right here means, this bracket here means that the A is included. This bracket here means that the B is included. When we don't want to include endpoints, we use parentheses. So we use brackets when we want the endpoints included, like we have here. So let me start over since I wanted to explain that. A continuous function f defined over a closed interval, bracket A comma B bracket, must have an absolute maximum value and an absolute minimum value over AB. So if you're working over a closed interval, if you're working on a closed interval where you've got the brackets, you know that you're going to have an absolute maximum value, that is a y value, and an absolute minimum value, which is a y value, over that interval. So what that means is you will have an absolute maximum value, which is an f or a y value, if you want to look at it that way, and it will occur at some one or more x's inside this interval. It could occur that absolute maximum could occur at one of the endpoints, at A or at B, and sometimes they do. Or it could occur in the interval, or it could occur at more than one spot, more than one x in this interval. And also an absolute value over this interval, or an absolute minimum value over this interval. So you're guaranteed, if you have a closed interval, in an interval in this form here, you're guaranteed to have an absolute maximum value and an absolute minimum value. You're guaranteed to have both of them. Now let's talk about this maximum minimum principle number 1 in terms of what is a strategy? How do we find an absolute maximum and minimum values? How do we find those? It's very similar to what we did last time when we were finding relative extreme points. It turns out that when we're looking at absolute maximum or minimum values, we want to consider the candidates for relative extrema as part of our process. And those candidates are the critical numbers. So in order to find the critical numbers, that's a first derivative concept. So we first need to find the first derivative. Then we want to determine all critical numbers in A, B, in this closed interval. How do we determine critical numbers? That is, for all C in this given closed interval, we want to find all of those for which the first derivative is 0 or the first derivative does not exist. So that's what we did. That's how we start, exactly how we started when we were looking for relative extreme points. So the beginning of the process is exactly the same. And then you'll see me do this in table format, but just to give you a taste of what this process is like, you then in this third step is to list all the values from step B, in other words, all the critical numbers and points of the interval. So if we go back, we want to list all of our critical numbers and we want to list the endpoints in our interval, A, B. So you'll notice there's A and B here. And then ever how many critical numbers you find. They've covered, they've got a lot, they've got quite more than we're going to have to find in here. And then what we're looking for is we're looking for the absolute maximum Y value and the absolute minimum Y value. So we're looking for Y values. So when we have our list here, we then have to find the Y's associated with one of these X's. These are critical number, these endpoints, A and B are X's. These critical numbers are all X's here. So we are looking at, we're interested in what is the largest Y value and what is the smallest Y value. So we then have to find the Y coordinate, if you will, associated with each one of these X coordinates. Turns out that the largest of these Y's is the absolute maximum of F over that interval closed AB. The smallest of these is the absolute minimum of F over our closed interval AB. So that's really the process. And I'm thinking about what I want to do now. Let me go on just a moment to make sure I are in where I want to be. Yes, I think I'm going to take a breather here and I want to look at a few problems. Let's take a look at a couple of problems. One of which we're going to do inside of, one or two of which we're going to do inside of my math lab, and then a third problem where I'm going to present using my notes that I've got down on my desktop. So I'm going to stop this for now. Let me remember how to stop it. It's been a week since I end show for now. We'll pick it back up here in a little bit. So we'll go into my lab math. And I was just in there. So I want to take a look at our homework. And just before I do that, let me just show you that I've posted a quiz under quizzes and tests. I posted quiz 4 this morning. It is due on the 26th and it's unavailable after stated due date. So that's very important quiz, because I usually look at the quizzes when I'm creating a test to see what kind of problems I put in the quizzes. So that's very important for you to do that. And of course, you can take that quiz as many times as you want. I would encourage you to do so as soon as you've got this section 3.4 assignment done, because you want to get a feeling for how difficult the quiz is. Since we're past derivatives now, we're getting into some of the more challenging topics in survey of calculus. You will see that it will definitely get more challenging. So I encourage you to at least get a feel for what's in that quiz and whether you think you can do it quickly or not. So for time management purposes, it's probably a great idea for you to look at the quiz as soon as possible. So let's go back to homework here. And you can see I've got today's assignment posted here. I did also post my notes. I've been posting my notes under homework and Bear Solutions. So if you have a question on a particular topic, let's say, and the learning aids in MyLab Math aren't working for you, or you prefer my homework solutions instead, this is where you go. You click on that and you can see they're all right down there according to section number. And you just click on whatever you want. So say you want 3.4, there are my notes that I am presenting today. So that's a nice little resource, and if students write to me, sometimes and ask me a question, sometimes I point them to my solutions. So homework, we want to work on our current homework, absolute max and mins. So I'll click on that. And I want to take a look at question 1 first. And I want to get a similar question. So I am a visual learner, and I thought it would be nice to take a look at a question having to do with a graph. And I think I might look at a second one here in a moment as well. So what does this question say? And I want to jot down maybe a few notes here. So find the absolute maximum and minimum values. Now that values means y values of the function, also means y, is another hint that we're talking about y's here, over the indicated interval, and indicate the x values at which they occur. So I'm going to write down the function f of x equals 4 plus 2x minus 2x squared over the closed interval 0 to positive 3. When I first went into this problem, what I noticed is, and let me just bring, and we'll have this go over here so we can see. What they're really wanting us to find is the absolute maximum value over this interval 0 to 3. Well, 0 to 3 is right here. So the points on the graph from 0 to 3 are these points on this red portion of the graph, and the red portion only. The dashed blue lines are not part of the graph. That, at least not the part that over the interval from 0 to 3. So we want to find the absolute maximum value and the x at which it occurs. At first, I tried to guess what the numbers were just by looking at the graph. It did not work for me. So you want to keep that in mind. So what you want to do is you want to find the critical numbers. You want to start by going through that process that we looked at in our PowerPoint. And just to remind us all of that, what was our process? This is the situation we're in. We have f, a continuous function defined over a closed interval. Define the absolute maximum and minimum values over AB. Do the following. First, find the first derivative. So let's find the first derivative. So if we want to find the first derivative of this function right here, the derivative of 4, that's an additive constant, is 0. This down. The derivative of 2x is 2 times the derivative of x, which is 1. So that's just 2. So f prime of x is equal to 2. And then this term, minus. And this 2 comes down, multiplies with this 2 to give us 4. And then x. We take the old power 2 and reduce it by 1, and we get a new power of 1. So the first derivative is 2 minus 4x. Now, that 2 minus 4x is defined for every x value. I can take any real number x, multiply it by 4, and subtract it from 2, and I'm in business. We don't have to look for where our function is undefined here. So what we need to do to find the critical numbers, remember you have to look for where the critical number, to find the critical numbers, you're looking for x's for which the first derivative equals 0, or for which the first derivative is undefined. We only have to look here for x's for which the first derivative is 0. So I'm going to put in 0 for f prime of x. And then on the right side, I'm going to have that 2 minus 4x that we just talked about. And we now want to solve for x. So I'm going to move minus 4x to the other side by adding 4x to both sides. I just want you to get the process down. So that will give me 4x equals 2. And now I want to divide both sides by, there's a 4 in front of the x, so I want to divide both sides by 4. So get x equals 2/4 is 1/2. So our critical number is 1/2. Okay. So what does that tell me? I'm looking at this over here, this red portion of the graph here. And I'm seeing that it looks quite possible that this is at 1/2. At an x coordinate, this point right here has an x coordinate of 1/2. That's what it looks like to me. The only other possibilities for a relative maximum are the endpoints of this interval, which are 0 and 3. So our only possibilities are 0, 3, and our critical number, which is 1/2. So that definitely looks like the x coordinate of this is 1/2. So we're going to go with that. So the x coordinate is 1/2. But we need to find the absolute maximum value. That's the y value. So how we find that absolute maximum value is we take the 1/2 and plug it into the original function. That's how we find all of our y's when we're talking about optimization, which is relative extrema and absolute extrema. So I'm going to take my calculator and I'm going to put in 1/2 into this function here. I'm going to find f of 1/2. So that would be 4 plus 2 times 4. Oh, wait a second. No, let me back up. I've got to think about what I'm doing. So let's start over. And I've got to quit here. Okay, so I'm going to clear off my home screen here. And we want to plug in 1/2 for each x that we see there. And we can consider that 1/2 to be 0.5. You do not want to round when you're talking about absolute extrema unless MyLab Math specifically tells you to round. But I know that 1/2 is exactly 0.5. So it might be easier to put that in here. 4 plus 2 times 0.5. minus 2 times, in parentheses, 0.5 squared, Mountain Peak squared. And I get 4.5. That's the y. So I've got x, our critical number that we're using, because in this case, the critical number it results in the absolute maximum value. So that's why we're using that here. In other problems, you might need to use one of the endpoints. So what I want to do now is go ahead and put in what we have and check it. The absolute maximum value we think is 4.5. And it occurs at x equals 1/2, which is 0.5. And it says below the boxes here, round to 2 decimal places as needed. So I'm going to put this in as this 1/2 in is 0.5. And then I'm going to take a peek back at the graph here, this red graph, and make sure that looks like it's reasonable. So we have already decided, I think, that the 0.5 is reasonable for x. But what about here? If we go straight over to the y-axis, that looks like it's halfway between 1, 2, 3, 4, and 5. So 4.5 looks like a good guess. And that's what we found. You could say exactly. We know it's 4.5. So let's go ahead and check this. So any questions on that particular problem?
I have a question.
Yes.
Not really just this problem, but in general. When you're talking about absolute max or relative max minimums, does it have to be curved?
Does it have to be curved?
Yeah.
Yeah, not necessarily. You could have straight lines.
So just a point at the top of a line could be considered an absolute max?
You could consider a straight line, like a horizontal straight line. You could consider that even though all the y values are the same, in theory, you could consider, you could have like a horizontal line going through y equals 2, for example. Or let's say y equals 10, or something up here, like this. And well, I guess I'm not under. So, okay. I mean, there are oddball cases like that. So I guess I can't just, as a mathematician, I can't just say curves, because what do you mean by a curve? To me, when we talk about graphing, I think of all graphs. And if I'm going to say something to a student, I have to consider all graphs, if that makes sense.
Okay. Well, I was asking, take for example the graph y equals x. It's a line that goes diagonal.
Right.
Maybe on the plane of 0 to 3, at the point 3 where it's the highest, would that be considered a max even though it's just a line?
Yes. Yes.
Okay.
Thank you for clarifying that. Yes, I see what you're saying. Now, we did the max on this problem, so let's do the min. So let's go back and take a look at this graph. Now we can visually see where the min is. It's the lowest point on the graph, which is right down here, right there, the lowest point. Remember, the red part of the graph is what we're looking at, because that corresponds to the interval 0 to 3. 0 to 3. So we are now looking at this point right down here. But that's easy for us to figure out. It's not as complicated as the first part. So if we want our x coordinate, we can go right back straight up to the x-axis, and it looks like it's at 5, 4, 3. It looks like it's at 3. So that's the x coordinate of our absolute minimum. Now we need to find the y coordinate. So the y coordinate, we can go straight over to the y-axis, and it looks like that's at -10, -9, -8. So it's a y of -8. So we're going to go over here and put those numbers in. The absolute minimum value is -8. And that occurs at an x coordinate of 3. Any questions on this particular problem? So I just wanted you to see one of those because it threw me when I first looked at these problems. We have a brand new book in Survey of Calculus this semester, and it threw me. And so I wanted to make sure I presented it to you so you could see how this worked. Next question. Let's see what it brings up here. I'm not sure if we're going to take a look at that. And you see they're stepping it up here a bit here. Now we're talking about this. And let's just talk about it here. Let me move this out of the way, and we have our answers over here. And I just think maybe I'll just verbally talk about this. I don't want to take a lot of time like we did with the first problem, but we're talking about this function over the interval -1 to 2. So this point here on this red graph is at an x. If I go straight down to the x-axis, that's at -1. This point right here, straight down to the x-axis, that's at 2. So we're talking about this interval. And what are we looking for? We're looking for the absolute maximum value, the highest point or points on our entire graph, because it's possible for this to turn again and then come back up. So you're going to have situations where you're going to have like this. We've got 2 values here. Okay, so we'll take a look at that in a moment. So the absolute maximum value is right here. The x is at 2. Check. The y is at 8. That's where that comes from. You could, I know they're a little light there, the answers. The absolute minimum value, the lowest point on the entire graph, is right here, but you can see you can go horizontally straight over and get another point as well. Both of those points have the same y coordinate. It is at 2. So the absolute minimum value is 2. Now, at what axis does that occur? Go straight down to the x-axis at -1, straight down to the x-axis, 1. So this absolute minimum value is 2, occurs at 2 different x values, -1 and 1. Any questions on this particular problem? Now, let's go into my notes here. I did write out 1 and 2 pretty thoroughly, like you would for other problems that we're going to do. Let's take a look at number 4. Number 4 states, find the absolute maximum and minimum values of each function over the indicated interval and indicate the x values at which they occur. What's very, very, very important is to realize that we're working on this interval. This means we start, if we're going from left to right along the x-axis, we include -2, and we want all the numbers in between -2 all the way to 0, including 0. The first thing I want to point out is when I found the critical numbers, I got 2 critical numbers, 3, or I got two critical numbers, yes, 3 and -5/3. Well, that 3, make sure I go back to the right problem. That 3 is not in this interval. This interval is -2 is less than or equal to x is less than or equal to 0. The +3 is not in that interval. So when that happens, we don't consider that +3. We're only interested in what's these x values right here. So what I had to do there is note for this 3, this is not in the given interval. So I ignored it. I put it in the table and again emphasize that it's not in the interval, but we don't even look at it. We really don't even need to put it in the table. And you might not want to put it in the table because it would cause confusion. So if one or both or of your critical numbers aren't in the interval, then you don't consider those. Every critical number has to be in this interval in order for you to consider it. If you may get a case like you will for this problem, likely get a number that is not in the interval. So you want to just cross it out. So let's do this problem according to the process that I presented on the slide. So the first thing we need to do is take the first derivative. 3x squared minus 4x minus 15 plus the derivative of 5 is 0. So now we need to find our critical numbers. Now you can attempt to factor this if you prefer to do it that way, or you can, since this is a quadratic here, and let me just first say we need to set our first derivative equal to 0 to find the critical numbers. So let's do that first before we get ahead of ourselves. And then you can use a quadratic formula only because you have a quadratic equation here. You have a polynomial and the highest power is a 2 on this side. And it's in descending power order, so we can identify the A, the B, and the C. And the quadratic formula says x equals negative b. B is -4. Plus or minus the square root of b, which is -4, in parentheses, and square it, because we want to square that negative sign as well. -4 is part of the quadratic formula, times a, which is 3, times 4ac, times c, which is -15. Then I always like to work inside the square root. And when I figured out what was inside, it turned out to be 196. The square root of 196, I did that on my calculator and saw that it was 14. So now what do we have? We've got negative of a negative is a positive, plus or minus 14, all over 2 times 3, which is 6. So we can break that up into two numbers. We choose the one with the plus sign first. That's 4 plus 14 over 6, comma, choose the one with the minus sign in it now, 4 minus 14 over 6. And then we can just figure out what these are. 4 plus 14 is 18 over 6, which is 3. 4 minus 14 is -10 over 6, which reduces to -5/3. You can math frac on the calculator to get that. So these are our critical numbers. We did note before, and you want to check at this point to make sure to see whether each critical number is in the interval. This 3 is not, because it's past the here. Then the other one, -5/3, -5/3 as a decimal is -1. If I round, -1.7, which is definitely in this interval. So we definitely want to consider this critical number right here. So I just emphasized again that 3 is not in the interval, so we can ignore that. I created a t-table with x and y in it, and we're using our y, we're denoting as f of x, so that's why I put that here. So I first put the critical number in that's in the interval, -5/3. Then I put in the endpoints of the interval. They are -2 and 0. -2 and 0, right from here. Copied those down. And then we want to find the y coordinate of all of those numbers. And just to give you a sense of what the answers are, you see they want this answer in reduced fraction form. So it's very important. What I would suggest that you do is go into get your graphing calculators and go into y1 of your calculator, go into y equals, and put in our function here. So I'm going to put in x cubed minus 2x squared minus 15x plus 5. And I'm going to double check. These kind of problems have a lot of steps to them, so I don't want to make an error. I don't want to make an error anytime I do a problem, but especially not now. Okay, so what I'm going to do is I'm going to do a second mode to get back to the home screen. I'm doing a quit really, and that's above the mode key, and it's in the same color as my second key, so I'm going to do a second mode. Now I think I've talked about vars in this class, and this is a really good use of vars. Let me see if I've got my graphing calculator. So we want to use this vars right here when we're on the home screen. So let's do that. So I'm going to click on vars on my calculator. Want to right arrow over to y vars. Can't do that on this static calculator here. And then you want to hit enter, enter on your calculator. That's the button down here. Enter, enter. So it's vars, y vars, enter, enter. And that puts a y1 on the home screen. Why do we want a y1 on the home screen? Because that will allow us to rapidly find the y coordinates associated with each one of these x coordinates. Now, something else I want to show you is if you click on this math key in the first column here, fourth key down, you will see that it takes you to number 1 frac. That will convert to a fraction for you. So I'm just going to do a second mode to get back to the home screen. So then I've got just a y1 there, and now I want to put a parenthesis in there. So I'm going to type an opening parenthesis, and I'm going to put in -5/3. This first x that's important here. -5 division 3 closing parenthesis, and now I want a math frac. It's math in the first column, followed by enter, enter. And that gave me 535/27. That's the answer MyLab Math wants. The only reason I did this is because I wanted to compare to see what indeed was the absolute maximum. I'm not so sure if I just keep my fractions over here. So then I'm going to repeat this entry and repeat an entry. What you want is this entry in this last column, bottom row, this blue entry on my calculator. That's above a key. So I need to use my second key first. So I'm going to do a second enter. And that's just going to repeat the previous entry, but what I can do is I can back over it and clean it up to my heart's desire here and or I could just leave it and go inside the parentheses and just put a -2 this time. So I'm just going to change that -5 to a -2, and I'm going to delete. The delete key is right here on the calculator. I'm going to delete what's inside the parentheses there, and I'm going to convert to a fraction. It's not going to hurt. I need to change that -5 to a, I backed over, got the -5, and I need to change that to a -2. And I get 19. Now I'm going to repeat that entry again. Change that -2, this time to x equals 0. Delete that other character, enter, I get 5. So I actually took this fraction, 535 divided by 27, and got that it was approximately 19.81. I had no idea how this compared to this 19 right here. And I needed to know in order to correctly select the absolute maximum and absolute minimum. So this is indeed the largest of these y's here. So this one is indeed the largest one because it's 19.81. So this y value in this column is the absolute maximum value in the y column. That's what we're looking for. So the absolute max is 535 over 27. The absolute min, the smallest number of all the numbers you have in this column, is 5. That's the absolute minimum value. In other words, y value. And where do they occur? At the corresponding x value in the x column. So you can see that they wanted us to state them. The absolute maximum value is 535 over 27. And where does it occur? At -5/3. The absolute minimum value is 5. And where does it occur? At 0. Right there. Any questions on this particular problem, number 4? This is really the strategy on how these problems are done. So let's go back to the slideshow presentation and talk about another maximum minimum principle. And let me get right there. We looked at this already. Let's look at maximum minimum principle number 2. Now this has to do with open intervals, really, where you don't have those endpoints. For instance, this has to do with what happens if you're looking for the absolute maximum or minimum values over -infinity to +infinity, or 0, not including 0 to +infinity. That's what we're talking about here. Theorem 9, maximum minimum principle number 2. Suppose that f is a function such that f prime exists for every x in an interval and that there is exactly one critical value. Can't have 2 for this principle. Can only have one critical value in the interval and only one. And it's got to be inside the interval because you're going to have like you're not going to have endpoints like we had before. You could possibly have endpoints. Some of the problems may, as I recall. I'm just thinking because this is a new book to me. But what you're going to do, what really is going to be important is that you're only going to have exactly one critical value C in the interior of the interval, inside that interval, not at one of the endpoints, if they're included. And you're only going to have one critical value inside the interval. If you've got this principle doesn't apply. So this principle won't apply if you have two critical numbers interior of that interval. Then there is f of c is an absolute maximum if the second derivative at the critical number is less than 0. In other words, this tells us that second derivative tells us about concavity. When second derivative is less than 0, that means we have concave down, which means we'll have a relative maximum. And if the second derivative is positive, that means we're talking about concave up, in which case you'll have a relative minimum. That's what it's really saying to us. I don't think I want to take the time to go over the example in the slides. So let's just back up a bit, and if you want to copy that down, that might be helpful, definitely. And especially what's out there. This exactly one. Especially that. So I want to take a look at one or two problems in our homework instead. I think that's a better use of our class time. Let's take a look at problem number 9. Eight, 9. Let's take a look at this one. So problem number 9 states, find the absolute maximum and minimum values of the function, if they exist, over the indicated interval. Also, indicate the x value at which each extrema occurs. Extrema collectively is referred to absolute or relative extrema, which means both relative maximum, relative minima, absolute maxima, absolute minima are all in that when they say extrema. They don't, right here, it's not specified. Now up here it is specified, but down here it isn't. So what we are looking for are all the absolute extrema for this function. There are two. There's an absolute maximum and an absolute minimum, and they can occur at different x values. The same maximum, the same y value can be coming from the same x, from two different x values, two or more different x values. We've already seen that today. So what we want to do is find the absolute maximum and minimum values. So we want to do it for this function, f of x equals x squared plus 160 over x on the interval 0 to infinity. Now there's no brackets here. We have parentheses here. So we need to get started. So the first thing I'm going to do is rewrite this original function by bringing this x to the first in the denominator up. When you bring a base to an exponent up to the numerator, you just change the sign on the exponent only. So this x to the first becomes x to the -1 when it gets brought up. So we are now talking about a function of, our function is f of x equals x squared plus 160 x to the -1. And all I did is bring the x up in the denominator here. We want to, in order to find our critical numbers, which are part of this process, we need to take the first derivative. The first derivative is, the derivative of x squared is 2x. And then this negative is going to come down, meaning we're going to have a negative here. So I copied down that minus sign here. 160x, our new power is -1 minus 1, which is -2. We want to then, what do we want to do? when we find our critical numbers, we want to look to see where our first derivative is 0 or undefined, both of them. Those are both possibilities for critical numbers. Where is the first derivative 0 and where is the first derivative undefined? So let's start by making this first derivative equal to 0. I say that because there is going to be a place in this problem where we're going to need to look at where the first derivative is undefined. So let's start by looking where the first derivative is 0. So I take out the first derivative notation and put in 0. So 0 equals, copy this down, copy this down. Now it's a little difficult to work with a negative exponent. So what I did there is I flipped it back down to the denominator and changed the sign on only the exponent. Now we have 0 equals 2x minus 160 over x squared. Then what? I looked at this and said, well, let's get a common denominator. So if I multiply top and bottom, I want x squared in the numerator. I want x squared in this denominator right here. So how do we get x squared in that denominator? We can put it there, that x squared there, but then we also have to put the x squared in the numerator because we're really then dividing by 1. So I multiply top and bottom of this term only by x squared. That gives me 2x times x squared. So now we have x cubed because we have x to the first times x squared. So 1 plus 2 is 3. We're adding the x. We have like bases multiplied together. You add the exponents. So we get the original 1 plus 2, which is 3. And then there's an x squared down below, down here. So then we can just, since we have a common denominator, we can add the numerators. So we get 2x cubed minus 160 all over x squared. That's where I went with that. So now we can set the numerator equal to 0. This whole fraction is 0 only when the numerator is 0. So we look at where the numerator is 0. So that will be 0. Let's write this down. 2x cubed minus 160 equals 0. And then we're going to look at where the denominator is 0. That's also can result in a critical number. Very important. Remember, we have to look at where the first derivative is 0 or undefined. Well, this is undefined somewhere. Okay, so we want to look at where this denominator, x squared, is equal to 0. We cannot have division by 0. So we need to look to see where x squared is equal to 0. Well, x squared is going to be 0. If we take the square root of both, plus or minus the square root of both sides, we're going to get, that happens when x is 0. Now you notice that x equals 0. If I plugged it in here, I'd get division by 0. That means 0, and besides, it's not even in the domain in this interval. So we have to, it's not in the domain of f of x, so we don't even have to consider it. It's not even a critical number in this context of this problem. So that's what we're looking at. So we didn't finish this. Let's go ahead and finish this. We're going to solve this for x cubed. So we need to divide both sides by 2 here. That'll give us x cubed on this side. If we take 160 and divide it by 2, we get 80. We want to solve for x, so we need to take the cube root of both sides. If we take the cube root of this side, cube rooting undoes cubing, we just get x, and we can write the cube root of 80 like this. That is a critical number. Now, for purposes of being very precise here, you probably want to take your calculator and take 80 Mountain Peak, 1 divided by 3. The cube root is 1 over the index. Okay, so when you're talking about roots, it's 1 over this index. So this right here, this cube root means an exponent. It's 1/3. So I'm taking 80 and raising it to the 1/3. Why am I doing that? Because I want to make sure that number's in the interval. So if I go back here, I got 4.3088 and so on, but that is definitely in this interval. So that definitely means that this is a critical number. And I'm going to leave it like that because it's going to cancel nicely when we do the rest. Let's go back to our PowerPoint just to remind ourselves what we need to do as part of the process here. We've just found the critical number. And I noticed something here. So I wanted to, we are just looking for that critical number where f prime of c is 0. So technically we probably didn't need to go through that of looking at where the denominator is 0, but I'm glad I did it because that will come up in other problems where the maximum minimum problem principle number 2 does not apply. And you probably have already seen that in some of your problems. Now you'll notice we've done this top part right here. We want to decide whether we have an absolute maximum or absolute minimum. And that depends on the second derivative here. 2 primes means second derivative. So we need to decide whether our second derivative is less than 0 or greater than 0. So, and that would be, so let's go ahead and do that so you can see the process. So you'll notice down here for problem number 9, I'm now taking the second derivative right here. So let's go back to our first derivative, which is why it's so important to label. Labeling with notation really helps students do math correctly. It's important to label. So we're starting at the first derivative. We want to differentiate again. The derivative of 2x is just 2. 2. There's the second derivative. And then we want to differentiate this term so that minus 2 comes down, multiplies with that negative to give positive 2 times 160. So 2 times 160 is 320. And then x to the negative 3. So 320 go back up here. Yeah, let me just say, so I think I did, yeah, so this comes down. I need to think about what we're doing here. This comes down. So this is negative 2 times negative 160, which is 320. X to the negative 3. 320x to the negative 3. So then all I did is, I don't like to work with negative exponents, so I flipped this term here, this factor here rather, to the denominator and changed the sign on the exponent. Now back to the PowerPoint just to see, what are we looking for? We're wanting to figure out what's going on at what's going on with the second derivative at our critical number. That C means critical number. So our critical number is the cube root of 80. So I took out this x, inserted the cube root of 80 in its place. So we got cube root of 80 right here. But then that is cubed by this power 3 here. Well, what's nice is cube rooting undoes cubing. So all we're left with in that denominator is 80. So we get 2 plus 320 over 80, like that. And if we put this in our calculators correctly, we'll get 6. 6 is positive. So when you're talking about the second derivative, if you get a positive number, that means your original graph is concave up. When we're talking concave up, we're talking about a relative minimum, or in this case, sorry, an absolute minimum. I'm just we're just out of the habit, I guess. So we know our original graph has an absolute minimum in this case. So let's go back up here. So we have an absolute minimum. And we do not have, for the first part, we do not have an absolute maximum value. And I didn't fill out that part and should have, but I didn't. I overlooked that. I was focusing on what else I needed to do. So we need to fill this out, absolute minimum value. Now first, our x is right down here. It's this cube root of 80. It turned out to be, when I did that on my calculator, I took 80 to the 1 over 3 power to do that. I got 4.309. Fulfilling the rounding requirements. So that's our x at x equals 4.309. How do we get the y value? We go back to the original function. We take our x and we go back to our original function here and plug in 4.309. I would tend, as a math person, I would probably plug in what I got for the x, the exact value of x, because I'm not exactly sure how our new MyLab math course, how they're actually doing the rounding. It's usually, if in doubt, it's better to round and wait to round until the very end. So I don't remember what I did here, but I would probably take this cube root of 80 and plug it in here for x and here for x to get the corresponding absolute minimum value. Any questions on this particular problem? Anybody have any questions? So just while I'm here, test 2 is 1 week from today on Wednesday, 10/28. We'll spend some time reviewing on Monday, but not the whole class period, roughly half the class period. And I'll be asking you all for questions because that's how I can best help you, knowing what kind of questions you have. So if you want to send me a question using Ask My Instructor, that's fine. And I can talk about it, or you can just, I had a student today right before class ask me a question and we covered that. I just went into MyLab Math and covered it. So it's however you want to do it, but please bring your questions because that truly is the best way for me to help you. If you can help me help you, that's all the better. And that means, bring me a particular problem or a particular question on a problem or a particular question on my notes, whatever that is and however that works for you. So I just wanted to remind you that test 2 is 1 week from today. And we will have a remote class on Monday, but Wednesday of next week will be your day to take the test. So if you have any special, like you've got 2 tests on that day, for example, and they're going to possibly overlap, please shoot me an email about that. So let's go back to the PowerPoint for a second. I think we're good on that. We don't need to do that. I've got a little bit more time here. So let's go back to my notes, and I put down a question mark by 11. I didn't know if I'd have time enough to cover it. So let's take a look at number 11. This is a very interesting problem. My husband and I, is also, I met him in math graduate school. And so you know, we have interesting math discussions from time to time. We had a very interesting discussion about this problem. So let me read it first. For a dosage of X cubic centimeters, cc, of a certain drug, the resulting blood pressure B is approximated by the function below. Find the maximum blood pressure and the dosage at which it occurs. Now you notice, here's our blood pressure function here. And you will see that the interval is 0 less than or equal to X, less than or equal to 0.12. But when in the context of this problem, what is X? X is the cc, the dosage of a drug. If you're really not interested if you're talking about zero dosage. So we can consider this an open interval and for the purposes of this problem. And what does 0.12 mean? It means that you're going to give that patient or all of the drug, but that's impossible usually to get all of the drug out of a particular syringe. You get almost all of it, but it's impossible to do that. So you can really consider this as on an open interval. So in the context of an application problem, you can make certain assumptions at certain times. So what do we want to do here? We're looking for the maximum dosage, and they tell us that. So we know we're looking for a maximum. And we're looking for the maximum blood pressure obtained. So let's find the maximum dosage first. This is our blood pressure function, B of X. Our X is the dosage amount. So let's start by taking the derivative. This 2 comes down, gives us 2 times 400 is 800. Minus this 3 comes down, multiplies with 3,200 to give us 9,600. X, reduce the power by 1 and get X squared. So we're looking for our critical number here. So I looked at both of these and I said, well, gee, let me just go for the gusto and see if I can take 9,600 and divide it by 800. So I did that on my calculator. And I got 12. So I said, okay, I can take 800 out of both of these terms, this one and this one. We've got an X here and we've got 2 X's here, so we can certainly take an X out. So I wanted to take 800X out. Parentheses, that's only going to leave a 1 left here, minus. Remember that 96 divided by 800 is 12. That's where that 12 comes from. And we only took 1 X out front. We have another X left here. So to find the critical number, I'm going to take, and let me interject that maximum minimum principle number 2, the second one we looked at, does apply here because of in reality, because of the context of this problem, you're never going to actually get to this 0, or you're not going to give a patient a 0 dose, and you're not going to reach this because there's going to be something left in the vial. So we can apply maximum minimum principle number 2 here. So we need to look to see where the critical number is 0. Or sorry, we need to find the critical numbers. And we need to set the first derivative equal to 0. So let's set this equal. When is this 0? When this factor X is 0. And when this factor 1 minus 12X is 0. These are what we call critical numbers. When I solved this, I got down to here. But we can ignore this one because we're never going to get there. So We're not interested in what happens at 0 in this context. So we really don't need to look at that. It's not a possibility, really. So we need to look at where 1 minus 12x is 0, however. And if we put the 12x on the other side, we get 1 equals 12x. And if we divide both sides by 12 now, we're going to get the 1/12 on this side equals x on this side. So we can use maximum minimum principle number 2. Take the second derivative. Our first derivative is right here. The derivative of this term is 800. The derivative of this term, 2 times 9600, is 19,200. And then reduce the power by 1 and get x to the first. Now we want to plug in our critical number. We want to know what's going on with the second derivative at our critical number 1/12. So we're going to plug it that 1/12 in here, and we get this. So I put this all in my calculator, and I came up with -800. When the second derivative is negative, that corresponds to the original graph being concave down. So we know that since this is concave, our original graph is concave down at an x-coordinate of 1/12, that we have we have an absolute maximum. I'm still getting out of that habit. Absolute maximum here. It's a relative maximum as well, but it's an absolute maximum in this case. And so we want to state our answers correctly. So let's see how we're going to state our answer here. We want the maximum is obtained for a dosage of. Now, dosage is an x-coordinate. So our dosage is 1/12. So what is 1/12? When I did that on my calculator, approximately equal to 0.08. Round to 2 decimal places. How do we get the maximum blood pressure? Well, here's our blood pressure function. We take 0.08 and we plug it in for x here and here, 2 different places. And you can see I worked that down here. And when I did all of that, I got 0.92 rounded to 2 decimal places. So I kept you over a minute. I'm sorry, but we got to a great place. And so I finished what I wanted to talk about today. Let me not forget to take attendance. Since I've had a week off from teaching, really, I want to make sure I'm doing everything correctly. Need to get back into the routine a little bit. That looks good. So if you have any questions, you're more than welcome to stay around for a few minutes. I do have another class at 10:30, so I'll just need to take a few minutes to myself. But you can stick around for 5 minutes or so and ask questions if you have any. So have a good day and welcome back. And we do have a remote class on Monday. And then next week you have your test, so we will not have a remote class that day. Remote class on Monday, though. Take care and stay safe. Bye for now. Elias or Dominic, do you have any questions? Turn the recording off.